What up, what up? It is Thursday, September 7th. It's my sister's birthday. I tried to call her, but she didn't answer, so I'm going to call her again. All right, right down there. Make sure you get that in there for the agenda. Pause it, because I'm moving on. Okay, cool. So go ahead and hopefully you got the agenda written down. I told you I was moving on. Now you're on this screen. Guess what you're going to have to do? Pause again. Try and solve both of these right here. And you are going to use this conversion unit right here, this conversion factor, this one right here. This is what you're actually going to use. So again, pause the screen, and then try and see if you can work through them, okay? Cool. All right, so this first one says convert 15 newtons into, so 15 newtons, right, in weight into pounds. So we're going from newtons to pounds, okay? So remember that. So I'm going to make myself bigger so we can kind of look at this thing. Okay, so I've already worked it out right here. So this is number one. So make sure you're just looking at number one. So we're going from 15 newtons, right? And I put that over 1. And then we're going to go ahead and go to pounds. So make sure that pounds is on top. Whatever unit you're converting to should be on the very top right there. And then you're going to have the conversion factor, which is the 4.45 newtons, right? And that is going to be equal to, so 15 times 1 is going to be equal to the 15 newtons on top. And then also, oh my gosh, this might either. And then also, 1 times 4.45. Now, we got to cancel the newtons, right? So that cancels, right? And then what we're going to be left with is this is canceled, this is canceled. What we're going to be left up here is with pounds, LBS. So because that newton canceled, so 15 times 1 pounds is equal to 15 pounds, okay? And then 1 times 4.45 is just 4.45. Now the number that comes out is this long number here, right? Something like this. And then you're just going to go ahead and say, well, since I had 2 plastic decimal places, that's where I'm going to round. So this 0 for less, let it rest. And then we're going to end up with 3.37 newtons, okay? That's what we're going to end up with. All right. This next one, right? We are going from, hold on, let's read it real quick. Oh my gosh. Oh, there it goes. Okay, cool. All right, so we're converting from 100 pounds in weight in 100 pounds, and then we're going to convert that into newtons, okay? Now, this one, 100 pounds, right? And then we have the pounds on the bottom, pounds on the top. That way we can cancel them. And it's just 100 times 4.45, and that is 445 newtons. So it's just 100 times the 4.45, and then you get 45 newtons. Now, most people, they're like, totally cool. I can work with that. All of that was good. I'm just going to go over this one more time because I feel like I went through it just a little bit fast there. So I'm just going to go through it again. So just remember, if we're starting with newtons, and that's what we started with, 15 newtons, okay? I just went like that. And then we're just going to put it over 1. And hopefully everyone should be comfortable with that by now because that's the same thing. All right, so we're going to multiply. And then since we're using that conversion factor, 1 newton is equal to 4.45, 1 pound, right? And maybe Mr. Farr should write that down. That's why I like having it written down because then I won't have to try and remember. 1 pound is equal to 4.45 newtons, okay? So then I'm going to put the 1 pounds on top. And the reason I'm putting that up there is because we're converting 2 pounds. Whatever you're converting to has to be on top. Then we'll put the 4.45 newtons on the bottom. And again, that's going to cancel, and that's going to cancel. And then now it's time to just do the math. So 15 times 1, again, that gives us the 15 lbs over. And then we're dividing that by 1 times 4.45, and that is the 4.45. That's what you'll enter into your calculator, and then you'll end up rounding that. And that's how we got to the 3.37 newtons. Sorry, not newtons. 3.37 pounds. That's how we got to that. Does that make sense? Hopefully this makes sense. Sorry I had it kind of cluttered at the beginning. Sometimes I'd be rushing. And so I was like, nah, let's go back and slow down. Okay? Hopefully this makes sense for you. And if not, reach out to me, let me know, leave a comment or something, like let me know somewhere. Send me an email, and then we can walk through it. Also, if you want to, you could just type in like Khan Academy, and then you could say how to convert from pounds to newtons, and they'll show you this conversion factor, right? And then they'll walk you through how to use it. So you can use YouTube kind of as an assistant if you're feeling any bit of confusion. Okay, cool. Also, if you want to be like, oh, I need to come in for the sting session with Mr. Farr, totally good. Request that. Some students did that. They requested to come in here because they knew that they needed extra help. Okay. When you need me, you throw me away. When you don't need me, you bring me back. What am I? Hopefully you got what this is. Some people were saying toilet paper. Some people said trash bag. But let's go here. The answer really is an anchor. So you throw an anchor out, and that's when you need it, but you pull it back up when you don't need it. All right, cool. So pause the screen, finish getting this all filled out. And then we're gonna go over it. Okay, we're gonna go over it. Okay, so this is the first time me using this on a video, so hopefully it works out well. So all I'm going to do right now is take the data from, and hopefully you got all that filled out. You took a couple minutes to get all that filled out. Answer the question to your best ability. We're going to go over all the questions right now. So hopefully you've got all this at least filled in, this part right here, and we're going to go ahead and fill that into our data table at this time. So I'm going to go, let's see if I can get this to work right. Okay, we're going to see if we can get it to work right. All right, so there we are right there. And then we're like, actually, you know what? I think we can make this zoom in a little bit more. I think it'll be easier. Yup, I think it'll be easier. But then, oh, what? Oh, there we go. So we can just come over right here. Boom. So we're gonna go ahead and write right in here. So this right here should be 1 newtons, and I don't like how thick that tip is. It's like doing too much. So I need it to be just a little bit smaller. Cool. And then this one was 2 newtons, and then this next one was 3 newtons. Okay, for sure. And then this one right here, we got 0.1 newtons. Okay, then we got 0.5 newtons. All right. Cool, and then this one was 0.8 newtons. All right, and then this last one was 100.3 grams. Okay, this last one was 198.9 grams. Now, just based off this, when it's 1 newtons, it's just about 100. When it's 2 newtons, it's really close to 200. So I'm gonna guess that this one right here, just based on the data, is that it's going to be 3, because it looks like it's about 100 grams per newton. You guys see that right there? So I'm going to go ahead and say that that's what I'm going to say. Based on the data, it looks like that's probably going to be 100 grams per newton. All right, cool. So we're going to have to be flipping back and forth between these things. So I'm going to go ahead and make this just a little bit smaller so we can see both of them at the same time. Then, okay, we're good there. Then we're just going to scroll up. The first one is, what is the difference between weight and mass? And we should write in something like the difference between, so mass, right, is how much stuff, right, is, or I should say is, in something, or say in, let's go with in, and let's go with object, right? By the way, I don't know why that big thing is in the middle right there. And weight is about how, right, how gravity pulls down on that stuff, or pulls down on the, we call it the mass. Okay, I'm going to squeeze that in right there. All right, cool. What is the relationship between weight and mass? So if we look at this relationship, it looks like as weight, because weight goes from 1 newtons to 2 newtons to 3 newtons, and it looks like mass is going 100, 200, 300. It looks like as oh, whoops. I don't know why I spelled it like that. As, my goodness. mass increases, right? Increases or goes up, then it seems like weight, weight. By the way, your handwriting better be better than mine. Also increases. I'm writing on some sort of crazy pad and a digital like thing. Also increases. All right, cool. Now, using data, predict, right, what a 400-gram bag should weigh. Okay, so look. So now we're going to go over here. We're going to come back over here. And let me move myself a little bit. Okay, so if we had, let's just see if we can fill this in. So if we had a thing like this, right? If it was like, whoop, sorry, that's looking crazy. And it was like blop, and then blop, and then this was 400 down here, right? 400 grams. What do we think this would be? So it goes 100, 198. It's really close to 200. Then this is 300, and we said this was 400. Then what would it be right here? What is the pattern? 1 newtons, 2 newtons, 3 newtons, and hopefully you found, oh, it's 4 newtons, right? That's what I'm hoping that you found. And a conversion factor really could be 1 newton is equal to about, what it seems like is 100 grams. So this would be between weight and mass. And some of you guys actually saw that because it was actually on your spring scale. It actually showed that, like if you looked at both sides. Use your data to predict. Oh, we did that. And so we're going to put in there, it would be 4 newtons. Okay, cool. What is the relationship between the mass of an object and the amount of force required to drag it? Okay, let's take a look. So it looks like as the force is going up, and again, same correlation as the mass is going up. So it seems like the more massive an object is, the more force that it's going to take to pull it, right? And hopefully that makes total sense, because that means so if you had an empty dresser and you had to pull it, it would be one way. But if you stuffed clothes inside of it and tried to pull that same dresser, now you're going to have to use more force in order to get it to move. And that's exactly what we're saying. We're saying the more mass or the more stuff something is made out of, then the more force that is needed, right? So what I would say is the more, I guess I'm getting a little bit better, right? The more mass an object has, then the more force is needed to move it. Okay. All right, cool. All right. Based on your data, how much force do you predict a 400-gram bag would be required to pull it across the table? So that's the last one, right? That's the last one. So that is just going back here, and that's saying if we filled this in. So it looks like from here to here, it looks like it's going up like 0.4 newtons, and then from here to here, it's like 0.3. So I'm just going to split the difference and say 0. Scratch that. 0.8 newtons plus 0.35 newtons. It's going to be equal to 1.15 newtons. And that's what I'm going to guesstimate. It's going to be 1.15 newtons, because that's about the change, the average change from both of these. So I'm going to put 1.15 newtons. That is my guess. That is my guesstimate. And that's how I got there. Now, hopefully that all makes sense for you. Again, we're letting the data dictate what we see and what we're predicting. By the way, this is a very important point. This is literally how science works. You'll get so much data from experiments, but then you're going to predict things that you haven't done. That's how science works. Now, does that mean it's 100%? No, but does that mean it's pretty likely? Yeah, it's probably, we got a pretty good chance that that is what it's going to be. So, and I'm willing to bet if we had a 400-gram bag, like if we put 400 grams of sand in a bag, and then we had to pull it, that I'm willing to bet that the force required would be around that amount, and that the amount that it would weigh in newtons would be around 4 newtons. So, and maybe we'll do that tomorrow in class, if I've got time, because we're already starting a new lab. So, all right, so we're going to pause here. We're going to take a few notes, and then we're out of here. We're almost done. So we walked through that entire thing, so that entire assignment, and, yeah, so make sure to get that all the way turned in. Sorry for saying, blah, trying to get rid of that. But, yeah, go ahead and get this turned in. You just have to scan it as a PDF and turn it in. The assignment is in modules per normal. All right, here. Go ahead and take this note. So pause the screen and take the note. I'm going to explain it right now. So interacting objects. These are objects that can affect one another. So here's an object. Here is another object, right? Here's another object. And when these come into contact, now we're going to call them interacting objects. Just like right here with the bowling ball and the pins, you can see that the bowling ball is moving. The pins are not. So the bowling ball is in motion because it's moving from one point to another. The pins are not in motion, but once the bowling ball hits those pins, boom, they become in motion, and something happens to the ball. So something's going on when they, and we're going to define this word, when this collision or when they collide and they become interacting objects. Something is going on there. So just go ahead and pause the screen and get, well, or if you already wrote it down, totally good. But just realize what we're going to start doing is we're going to see phenomena or things happening, and then we're going to give you academic language to describe it and how we would describe it in science. All right, y'all, have a wonderful rest of your day. Peace.